Welcome to today's deep dive. I am really glad you decided to join us for this one.
Yeah, it's a great topic today.
It really is. Because whether you're actively managing a commercial fleet, maybe prepping a vessel for some remote expedition, or you're just someone who, appreciates understanding the crazy invisible infrastructure that keeps our modern world running, this analysis is totally custom tailored for you.
Absolutely.
We're taking a pretty comprehensive stack of technical documentation and distilling it down to the critical insights. And today, we're examining a really detailed operational guide provided by Marine Data Solutions.
Right, focusing on modern marine satellite communication.
Exactly. Our mission here is to explore how broadband connectivity at sea has evolved. We're talking about a transition from this incredibly cost-prohibitive, laggy luxury into a totally streamlined necessity.
A vital operational necessity at this point.
We'll look at the underlying architectures, the honestly dramatic shift in economics, and what all this means for anyone operating off the coast. So, okay, let's unpack this. Because establishing a reliable internet connection on a vessel isn't just a matter of pointing a dish at the sky.
No, not at all. You're dealing with a really harsh, dynamic environment. I mean, the platform itself is constantly pitching, rolling, and yawing in the water.
Right.
And that is the core engineering challenge here. Because on land, our networks rely on fixed infrastructure. A cell tower doesn't move.
Right. The fiber optic cables buried under the street definitely don't move.
Exactly. But the maritime environment just trips away all those constants. A vessel operating offshore has to transmit a highly focused radio frequency beam through atmospheric interference, mind you, just to intercept an orbiting satellite.
And maintain millimeter-precise alignment while doing it?
Yeah, while navigating through 10-foot swells or, severe weather.
The source material actually details this whole data journey. And while we all sort of vaguely know that satellite internet involves space, the operational execution is where the real complexity lies.
It really is.
Because your onboard antenna transmits the request up to the satellite, right? And then that satellite acts as relay, bouncing the signal down to a terrestrial ground station. Then that ground station actually interfaces directly with the global fiber optic internet backbone, grabs your data, beams it back up to the satellite, and finally the satellite targets your vessel's antenna to deliver it.
What's fascinating here is that this entire round trip, traversing tens of thousands of kilometers through the vacuum of space and the Earth's atmosphere, is executed in mere milliseconds.
It's wild to think about.
It really is. And this continuous invisible data loop has become the fundamental umbilical cord for modern maritime ops.
Yeah.
It handles everything. Critical navigational updates, real-time weather routing.
Continuous engine telemetry, right?
Exactly. Fleet coordination software. The reliability of that connection literally dictates the efficiency of the entire vessel.
But the quality of that connection is entirely dependent on the specific orbital architecture you deploy. And the guide outlines this distinct transition happening right now in the industry. It's essentially a changing of the guard.
A massive paradigm shift.
Because for decades, the standard has been traditional VSAT. That stands for Very Small Aperture Terminal, which relies on GEO satellites.
To set the baseline for us, walk us through the mechanics of that legacy GEO architecture.
Sure. So GEO stands for Geostationary Earth Orbit. These satellites are positioned at an altitude of roughly 35,786 kilometers above the equator.
That is a massive distance.
It is, but the physics behind that specific altitude is crucial. At 35,786 kilometers, the satellite's orbital period perfectly matches the rotational speed of the Earth.
Which means from the perspective of a vessel down on the water, that satellite appears to be parked in a fixed, stationary position in the sky. Correct.
Yeah.
And because they maintain that constant relative position, a single GEO satellite can cast a huge footprint. It covers a massive percentage of the Earth's surface.
So you don't need many of them.
Right. A constellation of just 3 or 4 of these satellites can provide near global coverage, excluding the extreme polar regions.
But there is a catch.
A big one. Relying on satellites parked that far away introduces some heavy physical limitations. And the most prominent one is latency.
Right, because even at the speed of light, distance matters.
Yes, it does.
The data has to travel roughly 36,000 kilometers up, 36,000 down to the ground station, and then do that entire trip again just to get the response back to the boat.
Precisely. That 4-way transit creates an unavoidable physical delay. In a traditional GEO VSAT system, you're typically looking at a latency of 600 to 800 milliseconds.
And to put that 800 millisecond delay into perspective for your daily operations out there, think about trying to conduct a voice call or a video conference.
Oh, it's painful.
We've all experienced that awkward delay where you finish a sentence, wait a full second in silence, and then both people start talking over each other at the exact same time.
Yeah, the classic "no, you go ahead" moment.
Exactly. It makes real-time interactive applications incredibly frustrating, if not totally impossible. Plus, the hardware required to maintain a lock on a satellite that far away while the boat is moving, it's substantial. This is why we see those giant, heavy dome antennas on commercial ships.
Right, those radome enclosures. They're protecting a highly complex piece of mechanical engineering inside.
What's actually inside those domes?
Inside, there's a parabolic dish mounted on a multi-axis stabilized pedestal. It uses sophisticated mechanical gyroscopes and high-torque motors to physically rotate and tilt the dish.
So it's constantly fighting the motion of the ocean.
Literally constantly counteracting the pitch and roll of the vessel to keep that beam locked onto the stationary satellite.
Sounds expensive to maintain.
Very. They're heavy, they draw significant power, and because they rely on all those moving mechanical parts, they require specialized, ongoing maintenance.
Which brings us to the modern challenges outlined in the Marine Data Solutions Guide. The industry is rapidly shifting toward low Earth orbit, or LEO systems. We're talking about networks like Starlink Maritime and OneWeb. The architectural philosophy here is completely different from the old GEO model.
It's a fundamental shift. Instead of relying on a few massive satellites parked tens of thousands of kilometers away, LEO networks utilize a decentralized constellation of thousands of smaller satellites.
And they operate much closer to the surface.
Much closer. We are looking at an altitude of just 500 to 2,000 kilometers.
But let me play devil's advocate for a second.
Sure.
If these LEO satellites are skimming that close to the Earth, they can't possibly match the planet's rotation. They must be moving across the sky at incredible speeds relative to a vessel on the water.
They are, roughly 17,000 miles per hour.
So doesn't that mean the connection is going to drop every few minutes the second a satellite passes over the horizon?
That would totally be the case if the system operated like traditional VSAT. But the tech has evolved to handle this. Because their footprint is much smaller, a vessel is constantly passing out of range of one satellite and into the range of another.
How does the boat keep up with that?
The system manages it through highly sophisticated, automated handoffs. Before the satellite you're currently connected to drops below the horizon, the network has already acquired and authenticated a connection with the next satellite coming into view.
And the antenna on the vessel handles that tracking without those heavy mechanical gyroscopes we talked about earlier.
Correct. Modern LEO systems typically utilize flat panel, phased array antennas.
Okay, phased array.
Yeah, instead of physically moving a dish with motors, a phased array uses software to electronically steer the radio beam.
That's incredible.
It can track a satellite moving at 17,000 miles per hour and instantly switch its beam to a new satellite in microseconds, all with zero moving parts.
Here's where it gets really interesting. Because you're communicating with a satellite that is only 500 kilometers away instead of 36,000 kilometers, the latency bottleneck is basically eliminated.
Evaporated.
The guide notes that LEO systems bring marine latency down to a highly responsive 20 to 40 milliseconds.
Which is huge.
That's entirely comparable to the terrestrial broadband connection you probably have in a land-based office right now. It suddenly unlocks the ability to run cloud-based operational software, remote desktop apps.
High-definition video conferencing without that agonizing audio delay.
Exactly.
It effectively removes the distinction between working onshore and working offshore. When you reduce latency to that degree, enterprise-grade IT infrastructure actually functions as intended.
Yeah.
But as profound as the technical improvements are, the shift in capital and operational expenditures is what is truly driving this massive adoption rate across the industry.
Let's transition into the financial realities because the contrast here is sharp. If you're out there budgeting to outfit a commercial vessel or a large yacht, the traditional VS hardware requires a serious upfront investment.
It's a huge pill to swallow.
The guide breaks down the capital expenditure for legacy GEO equipment, and you're looking at anywhere from $15,000 to $50,000 just to purchase the stabilized dome antenna and the below-deck control units.
And that capital expenditure is only the beginning.
Right.
The operational cost of leasing bandwidth on those legacy GEO satellites are notoriously high. Monthly service contracts for traditional VS typically range from $2,500 to $10,000
Per month.
per month. Keep in mind that premium pricing does secure highly reliable global coverage, but it often comes with strict data caps and the high latency we discussed.
So you're paying enterprise rates for a connection that basically struggles with modern, data-heavy applications.
Exactly.
Compare that to the deployment costs for the newer LEO architectures. The hardware barrier to entry has plummeted. Purchasing a modern flat panel array costs a fraction of the legacy gear.
A tiny fraction.
It generally falls between $2,000 and $5,000. And the operational expenditures are similarly scaled down. Monthly service fees become highly adaptable based on your actual data requirements, ranging from roughly $250 to $2,000 or more for priority commercial tiers.
It completely democratizes high-speed connectivity.
Yeah, it really does.
Because historically, only large-scale commercial shipping ops, the military, or massive offshore energy platforms could justify the cost of satellite broadband.
Right.
By drastically lowering both the hardware and the monthly service costs, advanced connectivity is now viable for regional workboats, mid-sized research vessels, and the broader yachting sector.
To really illustrate the operational impact of this, the guide provides an excellent real-world case study. It focuses on a 100-foot charter yacht operating primarily between Florida and the Bahamas. Now, in the charter market, the guest experience is paramount. Clients stepping onto a luxury vessel today just expect their digital lives to continue uninterrupted.
That's right.
They want to stream media, conduct remote business, manage their ops without ever thinking about the underlying technology.
Right. The expectation of seamless connectivity doesn't just disappear because the vessel leaves the dock.
Exactly. So in this specific case study, the yacht was previously outfitted with a legacy VSAT system. The management was paying approximately $6,000 every single month for the service.
Ouch.
And despite that high cost, the connection provided highly limited bandwidth.
Which naturally creates operational friction.
Oh, big time. The crew is dealing with frustrated guests experiencing constant buffering on basic apps, and the management company is bleeding $72,000 a year for an underperforming asset.
So what did they do?
They executed an infrastructure overhaul. They decommissioned the legacy VS system and upgraded to a modern LEO satellite platform. But they didn't stop there. They integrated it with a dedicated cellular backup system. The financial result of that upgrade is striking. Their monthly operational cost dropped from $6,000 down to roughly $1,400.
That is wild. They reduced their monthly expenditure by over 75%, while simultaneously delivering a product with significantly higher throughput and lower latency to the end user.
Exactly.
It's a rare scenario in maritime ops where a cost reduction measure actually results in a vastly superior technical capability.
Normally you get what you pay for, right?
Right.
And before we dive deeper into that specific cellular integration they used, I want to highlight a fun, localized Easter egg from the source material for anyone operating near major maritime hubs.
Oh, yeah.
If your vessel happens to be based in South Florida, specifically near the Lauderdale Marine Center, Marine Data Solutions actually applies 10% of your equipment purchase directly toward professional installation.
That's a great detail. And it isn't just a promotional thing. It underscores a critical operational reality. Bolting a high-tech phased array to a radar arch is not a DIY weekend project.
Definitely not.
Professional installation is absolutely vital for long-term reliability. The marine environment is aggressively corrosive. You have constant salt ingress, extreme UV exposure, and relentless vibration from the vessel's propulsion systems.
Right. It's brutal out there.
It is. If the antenna placement suffers from structural blockage, or if the network integration below deck isn't properly configured, you will never achieve the performance specs the hardware is actually capable of.
So, what does this all mean for a fleet manager or a vessel owner who needs to specify a new communication package today? We have the established reliability of GEO systems, the low latency speeds of the new LEO constellations, and terrestrial cellular networks near the coast. How do you design an optimal architecture?
The key takeaway from current operational standards is that relying on a single connection path is a vulnerability.
Makes sense.
The most resilient infrastructure utilizes what we call a hybrid configuration.
Okay, hybrid.
Yes. This approach blends modern LEO satellite networks like Starlink or OneWeb with high-speed 5G and LTE cellular networks.
This is where specialized routing hardware becomes the brain of the operation. The guide specifically mentions devices like the MDS Blender or enterprise-grade PepLink routers. These aren't just your basic Wi-Fi routers you have at home. They handle complex SD-WAN operations, which stands for Software-Defined Wide Area Network.
Exactly. These routers act as intelligent traffic controllers. They utilize packet-level bonding and automated failover protocols.
How does that work in practice?
Well, for example, if your vessel is navigating near a major port or cruising along the coastline, the router will recognize the availability of a high-bandwidth 5G cellular network.
Oops.
It will automatically route heavy data traffic like guest streaming or large file transfers over the lower-cost cellular connection, preserving your satellite data allocation.
Oh, that's smart. And the moment that vessel pushes further offshore and the cellular signal begins to degrade, the router doesn't drop the connection. It seamlessly shifts the data packets over to the LEO satellite network. The crew and the guests utilizing the network don't even experience a disruption. The transition just happens in the background.
Right. Furthermore, for vessels operating in extreme environments such as high-latitude polar expeditions or critical commercial routes where absolute unbroken global coverage is non-negotiable, a hybrid system might still incorporate a traditional GEO VSAT terminal as the ultimate failsafe.
Really? So keeping the old tech around just in case.
Exactly. If the LEO constellation experiences an outage or weather-related attenuation, the system falls back to the legacy GEO network. It's all about layering redundancies.
The guide outlines 3 specific steps for designing one of these custom hybrid systems.
Right.
First, define the operational profile and cruising region. A vessel crossing the Pacific obviously has vastly different requirements than one operating exclusively in the Mediterranean.
Makes total sense.
Second, accurately audit the bandwidth requirements. You have to estimate the concurrent data usage of the crew's operational software and the guests' entertainment needs.
And the final step is selecting the appropriate hardware architecture to meet those specific needs. Ensuring the vessel has sufficient power capacity and structural mounting space for the integrated antennas.
Right.
Because thorough upfront engineering prevents costly operational failures at sea.
We have covered a significant amount of technical ground in this analysis. To sort of summarize the operational shift we're seeing, the maritime industry is rapidly moving away from exclusively relying on high-cost, high-latency mechanical dome antennas.
Yeah, that era is ending.
The new standard leverages compact, flat-panel phase arrays connected to low Earth orbit constellations, intelligently bonded with coastal cellular networks.
Exactly.
Whether you are optimizing fuel routing for a commercial fleet, supporting scientific research offshore, or managing luxury charters, understanding this infrastructure is essential. It proves that even in the most isolated maritime environments, a vessel can remain fully integrated into the global digital ecosystem.
If we connect this to the bigger picture, marine satellite broadband is no longer viewed as a supplementary crew amenity or just a redundant safety feature.
It's much more than that now.
It has evolved into core infrastructure. It's the prerequisite that allows the maritime sector to adopt cloud computing, remote diagnostics, and real-time data analytics. It fundamentally modernizes how a vessel is managed and maintained.
Absolutely.
This raises an important question, however, regarding the human element of this technological leap.
It certainly does, and it's a fascinating concept to consider as we wrap up today. For centuries, the very act of casting off lines and heading out to sea inherently meant severing ties with the terrestrial world.
You were truly off the grid.
Right. The isolation of the ocean provided a natural physical barrier against the constant demands, communications, and just the pace of land-based society.
Right.
Seafaring had a distinct culture built around that necessary self-reliance and disconnection.
It really did.
But today, a vessel operating in the middle of the ocean can possess a network infrastructure that rivals a corporate headquarters. If the crew can participate in live video conferences and stream high-definition media thousands of miles from the nearest shore, well, how does that always-on connectivity alter the psychological experience of being at sea?
It's a great question.
If the digital tethers are never truly cut, have we engineered away our ability to find true isolation on the water? It is definitely something to consider the next time you are looking out at the horizon.
For sure.
Thank you for joining us for this deep dive. Keep analyzing the systems around you, and we will catch you on the next one.